is going to tell us about yet another approach to binders and syntax.
Yes, thank you, Tej. And I know this is an exciting talk about yet another, new way to build a mousetrap. But yeah, it's a talk about a sort of a new library based on at least a quarter-century-old ideas. And yes, obviously, for a lot of us, we may think that syntax is a solved problem, solved issue. It took us a while. If you look at the early approaches to syntax of logic and programming languages, 100, 120 years ago, it was a bit of a mess. It's got better, certainly. And obviously, okay, so a solved problem, right? So it's easy, just use, and depending on who you ask, you can get a host of different ideas, right? Just use HOAS, or the abstract syntax, or just use autosubs, so fancy the Brown-based, the Brown index-based approach to syntax, or just use nominal techniques, just use locally nameless, just use, fancy universes of syntax. And the list goes on. So I will attempt to add to this list yet another approach based on functorial interpretations of syntax with binding. And there is a very sensible question whether we really do need more. I would argue that, yes, we can, in fact, learn at least learn something from the idea that there may be, other not fully explored approaches to syntax. And yeah, as you can see, the proliferation of standards reminds us, I think, of the proliferation of approaches to syntax. Now, as I said, this is work based on pretty old approach, and we need to go way back to the last century, back to 1999, as it turns out, where two papers were published. On one side, Marcelo Fiore with Gordon Plotkin and Turi published a paper on whose theory, I suppose, this library is based. And this is a paper on abstract syntax, where the syntax is represented as special kinds of functors with appropriate monadic actions. And I won't go into too much detail about, the background mathematics of all that. This is the basis for general theory. On the other side, in JFP, Richard Bird and Patterson published a different paper that turns out to be very closely related. And it's a paper about a relatively simple observation that in Haskell, in 99 Haskell, you could use nested types in order to mimic the Brown indices, right? So the Brown indices, as we know them, of course, are not necessarily representable in Haskell, or at least you'd have to jump through, well, they are now, but they weren't in 1999. This is before GADTs were first introduced and all that line of work. So, and even today, you'd have to jump through some hoops, right? So the idea there is, well, you could index your type with the type of variables, right? And the representation, they say basically, with what Haskell gives us, we can write certain functions on these types. We need quite a sophisticated type system in order to write all the functions that are interesting, in particular substitution and appropriate folds over these sorts of types. But of course, if we're talking about Coq, we have a system that's at least as strong as we need it, right? Probably even stronger. So the idea is that we can sort of join the two approaches in this middle ground of interactive theorem proving or dependent type theory, and from Bird and Patterson we can take the representation, basically adopting their representation or something that will at least look very similar, and because they don't really do any of the proofs or any of the theory, we can look to the more mathematical side and this whole notion of presheaves or special functors with appropriate actions and how they work as the representation of syntax and how they provide us with the theory of syntax for the theoretical underpinnings, for the proofs, for all the nice things. So how does it look really? Well, the representation looks like this in Coq. We can take an inductive type of lambda terms, over some set of variables. I think it may be a little bit better visible here, right? So we parameterize our type of terms with a set of variables. And then a variable is simply drawn from that set, and an application behaves like an application does. The set of free variables on both sides is the same. Now, the interesting bit happens in the lambda abstraction as usual, and the point is if we want to have a lambda term over a set of variable x, well, we need one more variable in the body, like we do with the Brown representation or any other similar representation, right? So in this case, we use a special type constructor, which is basically maybe, right? In order to say, well, I have one extra free variable in the body, and this variable is bound by the constructor. So this is the representation of Bird and Patterson. Of course, the set would not be there because it's Haskell, but other than that, this is basically the same constructor. And then the point is, in order to build a representation of syntax over this, we need to prove or show that the TM, the type of terms, is functorial in its parameter. So if we take two sets and a function between them, we can map that function over the entire type of terms. And we need to build an appropriate monadic action that will model parallel substitution. So this needs to be done in one step after the other, and this is again related to some of the ideas that came from early approaches to sort of proof engineering in the lambda calculus or in dependent type theory, also in the 90s. And so, okay, so this is all well and good, but where's the library, right? We can just, take our type of terms, do whatever definition thing we need, and it's there, right? Well, a question that we could ask ourselves is, this is nice, this is, a well-scoped representation. Can you make it well-typed intrinsically, right? And it turns out that you can, if you change the types appropriately, right? So this is a much more complicated definition, mostly because it's a type of terms that carries much more information with it. So instead of parameterizing it with a simple set, we're parameterizing it, our type of terms, with a context that carries some domain and types associated with the variables in that domain. And we're not producing a set, we're actually producing an indexed type that's indexed by the type of our term. And you can see it clearly in the variable case where we say, if I have an element of the domain of our context, I get a term over gamma of type gamma of x, right? And then the lambda and application case follow the usual typing rules. In the application case, I now have to take one type that's, one term that has an arrow type and another term that has the appropriate argument type, and I get a term of the return type, and vice versa in the lambda case with an appropriate extension of the context. And in essence, what happens here is we have the same pattern. We can ensure functoriality in the same way as we would in this sort of well-scoped case. We can give similar monadic action. There's some tricks required that I will sort of sweep under a rug. Do ask me if you want to know. And the idea is, now if we have a library, we can use the same derived theorems, same tactics, same support for definitions that are both well-scoped and well-typed, it turns out. Well, question is, how can we do that? And the idea is that we can build or at least our idea is that we can build a hierarchy of type classes. So basically the underlying theories from the 90s, the support that we have in Coq for making it go nicely, not just building a chain of definitions, but actually be able to use them nicely. It does require some support that came in later than that. And the idea is that we can start by specifying these indexing categories which relate to either sets or contexts or possibly other things over which we will parameterize our types. Right? And these have to have appropriate structure. They have to be categories because that's how, well, basically because what we're realizing here is that idea of Fiore, Plotkin, and Turi of building syntax as functors. Now, functors go from some source category to some target category, and in this case, they all will go into the category of types because we're building inductive definitions of syntax. So, we have indexing categories for base, layer, and for substitutions, and these are part of the library. And then, the idea is the user will define the type, like we saw in these two examples, plus the appropriate functorial and monadic actions, and they'll need to prove some properties to show that these actually have the right shape. What the library does is it provides additional supplementary classes which encode things like single variable weakening, substitution, the things that you actually want to use these definitions with going forward, and derived properties, tactics, all the nice things we can now define once and for all. Now, the idea is that because of the way that the thing is set up, particularly because these indexing categories are specified just as classes, and then we can provide different specializations of them, we gain quite a bit of modularity and extensibility in the library. So in particular, we have a lot of choice in terms of indexing categories. So the one that we usually use is the category of sets and functions, which gives us a very nice, well-scoped representations, like the first one we saw. But because we're in a richer language than just Haskell, right, and because we could specify what we require from these indexing categories, we can also define an instantiation of the same library with contexts and context homomorphisms, which ensure that whatever we do with the domains of the contexts, the types match up as we modify them. And over the course of several years, we've used both these and other constructions. In particular, you can also build constructions on these. So we can have products of categories if we need to index our terms with two sorts of variables, that sorts of things. We're working on other representations. In particular, it's nice to have a nice representation of finite sets with functions for when we actually care that the support of our terms is finite. That is not usually needed, but sometimes it's nice to know that. And obviously, you can roll your own. So one of these nice consequences of this choice is that if you want, for instance, to have linear notion of syntax, you can replace the category of sets and functions, where you can weaken or contract as you want, with a category of sets and bijections. And the point is, because of the way that the hierarchy of type classes is set up, some of the things that you would get for sort of normal intuitionistic syntax, in particular single variable weakening and single variable substitution, which don't really make sense in a linear setting, will not be available to you, because you wouldn't be able to construct certain instances of type classes in this setting. But all the basic ones will be available. Another nice thing that we gain from this is an interaction between indexing categories. So for instance, you can have interaction between well-typed and well-scoped categories. Your syntax may be well-scoped, but it may interact with some typing information as well. And it allows us for flexible binding and substitution structures. In particular, we've used this for, I think, some lambda mu related formalizations where the context variables behave in a slightly non-standard way. And yeah, of course, it's got a lot of limitations as it is, because at some point you run into the usual problem with formalizations, where certain things become expressible, but very difficult to use in practice. And in my case, this was when I tried to see whether I can build a well-typed church-style system F representation, where you can only represent the completely well-typed system F terms, so polymorphic lambda calculus terms, which is possible, but basically the syntax becomes very difficult to use because of the complexity of the indexing category. So the other interesting consequence is the fact that the very definition of syntax as a functor gives us some useful notions. And one of these that we've noticed recently is that we can actually build certain constructions on functors, including in particular function space, which is sort of limited to well-behaved functions of certain shape. And this allows us to build things like normalization by evaluation algorithm within Coq. This has been done before, not necessarily in Coq, but certainly in Agda. A nice twist that we've recovered using this syntax, and precisely as a consequence of functoriality, is that we can get precisely the sort of interpretation that is necessary. So there is no need, you don't get too many functions in the function space, and so you don't need to reason post hoc. You get precisely the sort of representation of normalization by evaluation that you need. And there's possible other applications. So for instance, in translations to continuation passing style, there is usually some sort of need for interplay, safe interplay between continuations and scoping, and the idea is that hopefully functoriality of the continuations would allow you to safely plug it into a larger scope. So this is the rough idea of what we have, and there is definitely need for more automation. And because right now the system is rather heavy on boilerplate. So I can show you a simple definition here. So this is a definition of a variant of system T with values and expressions. And so this definition is precisely of the shape that we've seen on the slides. But of course, it's not enough to just give the definition like that. We need to then define all of our functorial actions and the monadic actions, the substitutions, and prove quite a bit of boilerplate. There is some automation support, so there are tactics for this that will take care of your proofs in most common cases, but you still need to make quite a few definitions like that. So I think I'm slowly running out of time. So if there's any questions, I'll be happy to answer. And if you'd like to know more, please talk to me.
Thanks. This looks like really interesting work. Have you looked at all at syntaxes with multiple types of variables that may need to interact, or?
Yeah, so in general, this sort of arose from whatever we were formalizing, Piotr and I were formalizing in the last 5 years or so. And we have had a formalization where we needed two different sorts of variables. This is possible. You get a little less for free than you would in a single variable case, because I think in a lot of cases it's very easy to figure out what the Functorial action should be just based on the shape of the type. But with the substitution, it can be a little bit more tricky. There can be some interaction. So you may need to do a little bit more legwork in terms of showing that your substitution behaves as it should, but it's actually, completely usable with the rest of the library. Once you're done with these definitions, the rest of the support, simplification support, and proofs, derived proofs generally work reasonably well.
All right, I think we're running out of time, so let's give a round of applause. And
Thank you very much.